Welcome back to our second lesson inside our logarithms and exponential chapter 3 in the textbook. Today we are starting section 3.2, dealing with logarithmic functions. Now, logarithmic functions and their graphs, this is a little newer to you guys. You probably had not seen this in previous classes, where in previous classes you at least seen exponential sum, you have an idea what they are, but logarithms you really haven't seen before. So we're going to take our time on this section, and what I'm going to do is split it into two pieces. So getting into our vocabulary will actually tell us what those two pieces are. So a logarithm is the inverse of an exponential. It gets a variable out of an exponent. We'll talk more about that when we talk about solving exponential and logarithmic functions in section 4. But for right now, that's just the basic definition we're going to go off of. So the common logarithmic function is a log with a base of 10. Now, I'm not going to keep saying logarithmic. You're going to hear me shorten it to log. So that's where we're going to start with video number 1 on this section and homework number 1 on this section. It's just dealing with log base 10. Now there are other ways to change your base. We'll talk about that actually some today, as we are going to be using the Desmos calculator, which makes change a base incredibly easy. We will talk about the formula for change a base in case you're using a different sort of calculator that does not make life so easy. We'll address that in section 3. But on the Desmos calculator, making that base whatever you want it to be is incredibly simple. So we're going to focus on log base 10 for this video. On our next video, we are going to learn about the natural logarithmic function. The natural log, also abbreviated LM, we'll see that in the next video, is a log with a base of 8. As I had said in our section 3.1 video, E is this number that we are going to be using. It comes up a lot in nature, and in fact it comes up so much with exponential functions. In the real world, they decided, hey, we assigned this numerical value to E. We also should have its own notation for how to get that exponent out of there using the natural logarithm. So, the logarithmic function with base A is the inverse of f of x is equal to a to the x. So if I have y is equal to log base a of x, this is read as log base a of x, this actually will turn into, or it can be rewritten as, now, whatever's in here is essentially the, actually no, let's start with here. This starts with base A. So that's going to start with A as being the base of the exponent. Whatever the log is equal to, that is the exponent itself. And what is inside the log is what that is equal to. So what this says is that, hey, the log base A of x is equal to y, so A to the y is equal to x. So it's asking you, hey, what do I need, what power do I need to take A to in order to get x? So I know this idea is seeming a little bit odd. Let's see it with some actual numbers. So let's start here with log base 4 of 64. What this is essentially asking me is, hey, 4 to what unknown power is equal to 64? Now, this is one we can do in our head. Well, I know 4 to the first power is 4. That's no good. 4 squared is 16. I'm getting a little closer, but still off. If I do 16 times 4, that does give me 64. So 4 cubed equals 64. So that means that the log base 4 of 64 is 3, since 4 cubed is equal to 64. So I can rewrite this log base 4 of 64 equals 3. That's the same as 4 cubed equals 64. I know this is seeming probably a little bit odd and strange. It's okay. That's why we're going to practice some with it and work with this. We're going to take our time. That's why this is getting split into 2 separate pieces instead of one large chunk. Let me double check. There. So, when evaluating logarithms, remember the log is the inverse of an exponent. That means, again, log base a of x is the exponent to which your base a needs to be raised to get x. So 4 needs to be raised to the third power to get 64. So let's look at, this was kind of an example here, but let's look at another one. So I'm going to look at one, again, we're going to use our own mind power to do, and then we're going to look at how to utilize the calculator. I'm going to show you how to put in the base. So really, for whatever base you wish to use, you can change it to what you need. So following along in the notes, this is example 1. So example 1 asks us to evaluate log base 5 of 125. So in all reality, that's equal to some unknown, some variable x. So really, this is saying 5 to the x is equal to 125. So now I'm going to take my time and go through. I'm just going to start checking my powers of 5. 5 to the first power is 5. Okay? Not what I want. 5 squared, 5 times 5 is 25. I'm still short of 125. So I had to keep working at this. So I'm just going to move up. I went 5 squared, now 5 cubed. Well, 5 cubed would be 5 times 5 times 5. So that's 25 times 5. 25 times 5 is indeed 125. So for this, based off of that fact, since I know 5 cubed equals 125, that means log base 5 of 1 125 is equal to 3. So in order to evaluate this, I'm actually going to show us how to do this on the calculator to confirm we got this correct. So in order to do this in the Desmos calculator, now I downloaded their scientific calculator to give me a slightly bigger screen and view. It's the same thing on the graphing calculator, so you don't need to download the scientific as well. You can type in the same way. So I want to go to function. So inside functions, I will see log. So here with this, I thought it would let me do, put log in there twice. So I can hit log. I'll teach you how to do change of base right now. Of 125 divided by, since my base is 5, I am now going to say the log of 5. And indeed, I get 3 typing that into the calculator. So hopefully with this change in projection mode, this is a little easier to read. So let me on here. So there is a slightly easier way to change base if we are using the calculator on with the graph. So if, again, I go to functions, it will be filed under miscellaneous, where it says log base A. If you click that, where there's a little subscript area, you can put the number 5 for your base, then move up here and type in 125. Since this graphing calculator seems to have that function over the scientific, I will be sticking with the graphing, even though it's a little bit smaller. Hopefully this projection mode does help. So log base 5 of 125 is equal to 3. So now, on to example 2. Example 2 is just, again, all about using the calculator. Example 2 asks for the log base 10 of 300. Now, I'm going to show why this is an issue right now. So, okay, I'm going to try and do this like I did this one in my head. Well, 10 to the first power is just 10. Okay, not the right number I need. 10 squared, 10 times 10, okay, that's 100. Now, still not what I need. If I do 10 cubed, 10 times 10, 100 times another 10, it's 1,000. Now, I judge from 100 to 1,000, 300, somewhere in the middle there, right? I know my answer is going to be 2 point something, but how am I going to do that with all these decimals? It seems unreasonable to use that. That's why we're going to utilize the calculator. So again, just like we did, I'm going to type in, I can use, again, function, go to miscellaneous, and I'm going to choose log base A. My base is 10, so let's type that in. And then I'm just going to type 300. So, as you can see here, we get a decimal of 2.4771. So that's not a very pretty number, right? That's going to be something that's very difficult to do in your head. Again, like I said, back before we utilized technology like this, there were literally tables made of this. We have the technology. We're not going to bother with that. This is something, hey, something like that. I don't care what class you're in. You're just going to grab the calculator and you're going to do it that way. So again, as I said yesterday, I would prefer 4 decimal places. So that will be, again, 2.4771. So that is utilizing the calculator. Now, there are some important properties of logs to know and remember. We will reiterate these properties tomorrow again with natural logs, but they hold true regardless of the logs you are doing. So it does not matter what your base is, it always works the same. So these are properties that are always true. Now I'm going to talk about where they come from. So here we know, first property, log base A of 1 is always equal to 0 because any number to the 0 power is 1. So let's write that down. So log base A of 1 is always equal to 0 because A to the 0 power is equal to 1. So that's using our exponents, seeing how that goes back to this. The next property we're going to look at is log base A of A. Log base A of A is equal to 1. What I'm saying here, hey, 5 to what power gives me 5? Well, 5 to the first power gives me 5. 20 to the first power gives me 20. So basically that comes down to because A to the first power is always equal to A. The next property we're going to look at, and this is going to actually come in very helpful in section 4 when we talk about undoing things. Log base A of A to the x is equal to x. So what it's saying here is, what's your exponent? What is your exponent here? So what it's saying is, hey, A to the x, A to the x. What's your exponent? This is getting into the inverse property, which says, we'll talk about that more actually in section 3, when we talk about how to manipulate these, and in section 4 when we talk about how to solve this. This is the inverse property. The explanation is a little more in depth. I want us to get focused on the main idea here. Property. Okay. And then the final one says that the log base A of x is equal to log base A of y. If they're equal to each other, then the numbers inside have to be equal to each other. So log base A of x is equal to log base A of y, then x has to equal y. So basically it's saying, hey, if I'm taking the log of either of these numbers, or if I'm taking the log of these and I'm getting the same result, since it is a one-to-one function, these numbers do have to be the same number. So x is equal to y. So let's look at an example of utilizing one of these properties. So if I say, this is our third example from this section, log base 7 of x is equal to 1. Hey, 7 to what? 7 to the first power gives me x. Well, 7 to the first power is just 7. So x equals 7. If you think about it, that goes back to this property here. Log base a of a is equal to 1. So if I'm base 7 and it's equal to 1, then I'm doing log base 7 of 7. So this will help us again as we're going through the homework. Let me quickly talk about that as I flip ahead in the textbook. The first group is about evaluating. That will be the first thing, the first two groups, first group's just about rewriting. So the rewriting will deal with example 1. Evaluating will deal with example 2. The group after that, that's more evaluating. Again, example 2, utilizing the calculator. Example 3 is going to deal with the last group there, or the next group. So one thing we have to do is also we're going to look at their graphs. So a logarithmic function is an increasing function across its domain. So I'm going to quickly pull up the graph on Desmos of the basic log base 10 of x. So I'm going to type it in. Y equals functions miscellaneous already there. Log base 10. And inside the parentheses, I'm going to put x. So we see this over here. It is constantly increasing. Now it's increasing very rapidly and then kind of seems to level off. It will have a vertical asymptote. It says a vertical. Our exponentials had a horizontal. So I have a vertical asymptote right here. And my domain now is restricted. My domain is x is greater than 0. So with logarithmic functions, we're always going to get an answer larger than, we always need to plug in answers that are larger than 0. Whereas exponential, we always got an answer that was bigger than 0. Our range is all real numbers. Even though this growth is slow, it is still increasing as my x's get large. Now this will have an x-intercept instead of a y-intercept at 1, 0. So this is a reflection of the graph y, not functions, y equals 10 to, not 0. Y equals 10 to the x. So if we notice, if I put in the line y, don't want y up there, y equals x, y equals, come on, y equals x, you'll see that this orange line and this teal line seem to be reflected over the purple line. So they are inverses of each other because they are a reflection over the line y equals x, as we had talked about inverse functions in chapter 1. We learned that they reflect over the line y equals x, basically flip-flopping your x and y values, and we see that is what's happening here. So let's write down some important information about those graphs. So again, this is all in the notes page. So for log base A, or y equals log base A of x, the domain is x is greater than 0, because we have a vertical asymptote at x equals, or sorry, y, no, I'm sorry, x equals 0, sorry about that. So x equals 0 is our vertical asymptote. Our domain, or sorry, we did domain, range is all real numbers and now I do have an x-intercept at 0, or sorry, that would be a y-intercept. 1, 0 is my x-intercept. So we are going to utilize this to help us draw a basic graph. Now we've learned how to shift things up, down, left, right. Those rules still apply to a logarithmic function. But for right now, we're just going to do a basic graph of f of x is equal to log base 3 of x. This is example 4 from the notes. So log, our function f of x is equal to log base 3 of x. So for sketching this, 1, 2, 3, we need to make sure here I'm not seeing any shifting, anything like that. So I know my y-intercept, or not my y-intercept, my x-intercept is 1, 0. So I'm going to plot that. Since I did no other shifting, I know my vertical asymptote is also x equals 0, or the y-axis. So what I'm going to do is show an increasing graph. I'm going to go along the asymptote here, then peel off. Remember, we need to be close to these asymptotes. I don't want you crossing over them or being far away. We get nice and close. We get a graph that looks something like that. Now, I'm going to leave us here right now for the first video on section 2 in chapter 3. So your homework that is related to this is on page 199. You are going to do 16 through 36 even. So use what was reviewed in this video and your notes to help you with that work. Thank you for tuning in again, and have a great day.